Hi, welcome to one and all. In this lecture, I will be talking on existence of finite Fourier series for periodic arithmetic functions. In this section, we will be mainly dealing with the three theorems, where the first theorem is the base of all the other two theorems. The first theorem is Lagrange's interpolation theorem. I hope you have heard about the Lagrange's interpolation polynomial. This is a polynomial which we obtain by using a set of points, a given set of points. We are having a given set of points. We can have a polynomial associated with this, or we can construct a polynomial associated with this, and that polynomial is usually called Lagrange's interpolation polynomial. And this theorem is associated with this. Let us go to the statement of the theorem. Let z0, z1, z2, etc., zk minus 1 be k distinct complex numbers, and let w0, w1, w2, etc., wk minus 1 be k complex numbers which need not be distinct. Then there is a unique polynomial p of z of degree less than or equal to k minus 1 such that p of zm is equal to wm for m equal to 0, 1, 2, 3, etc., k minus 1. So in this theorem, we have to show that corresponding to z0, z1, z2, etc., zk minus 1, which are k complex, distinct complex numbers, and corresponding to this distinct complex numbers, we have to find the k complex numbers which may not be distinct. That means some may be identical, such that that complex number, we can find some complex numbers w0, w1, etc., wk minus 1, and we can find a unique polynomial p of z of degree less or equal to k minus 1 such that p of zm is equal to w. That is, each point z0, z1, etc., at each point corresponding to z0 we have a w0, corresponding to z1 we have a w1. That means w1, this polynomial p will be passing through the points z0, w0, z1, w1, etc., zk minus 1, wk minus 1. This is what we have to prove. Now this is a step-by-step procedure to construct this Lagrange's interpolation polynomial. So the required polynomial, we call it as, the required polynomial is p of z, called the Lagrange's interpolation polynomial, can be constructed explicitly as follows. Let us take a function a of z, which is z minus z0 times z minus z1, etc., z minus zk minus 1. This is a polynomial of degree k minus 1. You have to remember that, the polynomial of degree k minus 1. Okay. Now let us construct another function am of z. Let am of z. This is also an assumption. Am of z is a of z by z minus m. For the sake of understanding, I have just elaborated the steps, and you can skip some steps while you write the exam. Anyhow, let am of z is a of z by z minus m. That means in this a of z, if you consider am of z, that z minus zm term won't be there. So we will see closely what is. So a naught of z is a of z by z minus z0. A1 of z is a of z by z minus z0. Ak minus 1 of z is a of z by z minus zk minus 1. And if we write the general term, we can see that am of z is a of z by z minus m, where you could see that here all the terms are present. Z minus z0, z minus z1, etc. Z minus zm minus 1 is there. Then z minus zm plus 1 is there. That is, z minus zm is not there. And finally z minus zk minus 1. Now if we, instead of z, if we substitute z0, a naught of z0, we can see that this is z0 minus z1, z0 minus z2, etc. z0 minus zk minus 1, because z0 minus z0 won't be there because of the construction. So this term will be not equal to 0, and all the other terms a0 of z1, it will be 0 because of this z1. When you put z1, you will get z1 minus z1 will be there, so this will become 0. So a0 of z1, a0 of z2, etc. will be 0. Similarly, a1 of z1 won't be 0, that is, it is not equal to 0, and z1 minus z0, z1 minus z2, etc. z1 minus zk minus 1. So here z1 minus z1 won't be there. Proceeding like this, we can see that am of zm is zm minus z0, zm minus z1, etc. zm minus zm minus 1, zm minus zm plus 1, etc. zm minus zk minus 1. Thus, we can see that this am of z is a polynomial of degree k minus 1 with the following properties. That am of zm is not equal to 0, that we have seen here. And also am of zj, if j is not equal to m, we can see that all these terms are 0. So that we can see here. Thus, if we write am of z by am of zm, we can see that this is nothing but this term by this term. So z minus z0 times z minus z1, etc. z minus zm minus 1, z minus zm plus 1, etc. z minus zk minus 1 divided by zm minus z0, zm minus z1, etc. zm minus zm minus 1, zm minus zm plus 1, etc. zm minus zk minus 1, which is a polynomial of degree k minus 1, because these terms are known. Zm, z0, etc. are known, but z is not known. So here there are total k minus 1 terms. It's a polynomial of degree k minus 1 which vanishes at each zj for j not equal to m. And has the value 1 at z. So if we put zm, then it has the value 1. Now we can write this as a polynomial. See, what is p of z? Now what is p of z? P of z can be written as a linear combination. We will take some suitable scalars w0, w1, etc. Then p of z is nothing but w0 a0 of z by a0 of z0 plus w1 a1 of z by a1 of z1 plus etc. wk minus 1 ak minus 1 of z by ak minus 1 of zk minus 1. So if we expand these terms, we will get like this, and clearly from here, if we put instead of z, if we put z0, we will see that this term will reduce to 1. That is, if we put zm here, this will become 1. In all the other cases, that will be going to 0. So thus we will get p of z0 is w0, p of z1 is w1, etc. p of zk minus 1 is wk minus 1. Therefore, the linear combination p of z is equal to sigma m equal to 0 to k minus 1 w am of z by am of zm is a polynomial of degree less or equal to k minus 1 with p of zj is equal to wj for each j. Now we have found out that there exists a polynomial which satisfies the condition p of zj equal to wj for each j. Now our aim is to show that there is no other polynomial which satisfies this condition. That is, for that we will have to prove the uniqueness. For proving the uniqueness, we assume that there is one more polynomial which has the same condition. That is, if there is another such polynomial, say q of z, with the condition that q of zj is equal to wj for each j, then clearly we can see that q of z0 is equal to w0, q of z1 is equal to w1, etc. q of z minus zk minus 1 is wk minus 1. If this happens, then we can see that the difference is also a polynomial. P of z minus q of z is also a polynomial which is clear that this is a polynomial, so which has k zeros. a polynomial of degree k minus 1 and it has k zeros. But the p of z minus q of z is a non-constant polynomial with a degree less or equal to k minus 1 and has more than k minus 1 solutions. So this won't happen because p of z minus 1, p of z minus q of z is a polynomial and has more than k solutions, more than k minus 1. That is, it has k solutions. If it has k solutions, then this is only possible when p of z minus q of z will have uh, p of z minus q of z is nothing but a zero polynomial. This is only possible. Only this p of z minus q of z has more than k minus 1 solution is only possible when p of z minus q of z is a zero polynomial. So therefore, the difference p of z minus q of z would vanish at the k distinct points, and hence p of z is equal to q of z. Since both polynomials have degree less than or equal to k minus 1. Hence, there is, our assumption was wrong. That is, we cannot say that there are two polynomials which satisfies the same or which passes through. We cannot find two different polynomials which passes through these points. So here we can say that there is a unique polynomial of z of degree less than or equal to k minus 1 such that p of zm is wm for m equal to 0, 1, 2, 3, etc. k minus 1. And hence the theorem. Hope you understood the theorems properly, and if you have any doubt, you just ask me or put it in the comment part, or you can call me also. Thank you very much for the patient listening.